before I forget, although just to those online, be warned, there's going to be a lot of like on your own work, pausing and stuff. So, but we'll see here. Here's what I handed out just now, but I thought it might be nice to have it print out because it was so hard to see on the screen last week. We're going to keep doing what we were doing, and like I said, we're going to get really good at it. Okay, so I'm changing the order of the first 2 points because I'm finding that as I'm I know, right? Rude. As I'm doing them, I find that it's easier to figure out what x and y have to be if I first figure out what the objective function is, right? If I want to maximize the profit, for example, and it takes into account some object A and some object B, then that's kind of a good starting point for figuring out what my x and y's have to be, because my objective function has to have an x and it has to have a y, and so do my constraints, right? We have to talk about x and y in both scenarios. Okay? So then I kind of use that to define x and y generically. Then identify all the constraints. That's the tricky part, right? To read the problem and figure out, okay, what are my constraints on the XY combinations, right? So we're going to do more practice today. We might even, well, we will. We're going to switch gears to a minimization problem. So far we've only worked on maximization problems, right? Trying to find the maximum profit, the maximum whatever. And so usually it's profit. And so now we're going to try to minimize something, right? And the same steps apply. Okay? You're going to draw all the constraints on the same graph. Right? Figure out which area of the graph satisfies all the constraints at the same time. That's your feasible set, right? Which is going to be a region. Once you have your feasible set, you can find the vertices of the feasible set. Right? And I want you, mostly for kind of a ease of marking later, I want you to label the vertices A, B, C, starting at the origin and then moving clockwise. Okay? Or kind of do them in some sort of order. Okay? Ideally, but clearly label them. Once you have the vertices, right, each vertex is going to be a combination of x, y, right, that satisfies all of these constraints that we've set up. And so then we evaluate the objective function at each vertex, right? And so you plug in that value of x and that value of y, right? And you figure out what the profit is, or in this case, P, which is probably profit, right? And so, right, all the points in the feasible set will work. They will satisfy all the constraints, but only one of them is going to give you a maximized value or a minimized value. And then you select the optimized solution, whether that's maximized or minimized, then you're done. Whee! Okay. This next one is a little bit tricky. I was thinking when I was doing these, we said last day that I wouldn't make you draw the lines, but maybe it's easier to draw the lines then no.
You lied to us.
Hey, I'm leaving it open to suggestions. Because, okay, so this, let's use this as practice then for if I don't make you draw the lines, imagine that these equations then are not on here. I know, right? Just paint some white over there. Well, and obviously the vertices. I guess I should have done this in your handout. Oh well. Can't win them all. Just pretend you don't have anything. Technically not even this, but let's not get crazy. Yeah. I know, so you want to draw them or you want me to draw them, and you have to match them to the equation. Let's do a practice. And was there a reason I hadn't shut this, shoved it over to the side? I'm recording. No one's complained about, well, actually I can't see the chat anyways, so I don't know if they've complained about not being able to hear me. Okay. Change it back to a normal pen here. I did them all on one sheet each so that you could work on the backs, which you'll probably need. Did you get that PDF that I? Yeah. Okay, good. Because I wasn't sure. Sometimes it sends, and I feel like sometimes it doesn't send. I don't know. Good. Cool. My iCloud storage is almost up, so that's why I was kind of worried. Not sure how that would affect it, but it could. Okay. We need to match these lines to the equations, right? And so what could we do? Well. Whenever I see, so here, there's no word problem. We're given the objective function here. We want to maximize p is equal to 10x plus 15y. I guess I should introduce the problem. And then the subject to, and these are the constraints that we're dealing with. Okay. Whenever I see these inequalities, I like to rewrite them in the form of y equals mx plus b. And so for a little bit, you can ignore the inequality and just treat it as an equal sign, right? And just because I prefer to work with lines that are in the form of y equals mx plus b, they all work, but let's say that, how about, oh, that's not how I wanted to erase that. There. Let's call this 1, 2, 3. X greater than or equal to 0 and y greater than or equal to 0 tells me right away that I need to be above this line and kind of to the right of the y-axis, right? So it just kind of restricts us to a nice quadrant on our graph. And that's going to be a go-to constraint for all of ours. Yeah.
For the x and y greater or equal to 0, do we need to be writing that down for every question?
No, you don't have to. Just because it's understood that you're not going to make a negative number of things, right? And especially can't sell a negative number of things. Take it all back. And so it's kind of implied. If you want to be super particular, yeah, you should. But no, I'm picky. I'm not that picky. Okay, so maybe, just maybe, I'll change the colors on these. Oh, no. Oh, no, oh, no, oh, no, oh, no. You've probably done it already. But here I am in Struggle City. There. And then I'll do color coordinated things. How about 2 and are those distinct enough? Is the yellow hard to see in the back or you can see it? Okay. Guess it's kind of like an orangey yellow. Line number 1. Let's start with x plus y is greater than or equal to 1. Let's just start and write it all out properly. I'm going to draw the line at y equals 1 minus x. It's kind of swapping out the greater than or equal to with an equal sign. The equal sign just makes the line, and the inequality tells me which area of the line I want to be looking at, right? Which area satisfies the inequality. But for now, we need that that fence line, right, to figure out which side we want to be on. So that's why you can just replace them with an equal sign. What are my go-to moves for drawing a line? Well, I can plug in x equals 0. That might be a nice thing, right? X equals 0 puts me at y equals 1. So I know, okay, assuming the scale here is 1, right? 1, 1, 1, 1, 1. Might be nice to figure out what the x-intercept is, right? If you plug in y equals 0, then what does x have to be? In order to make y 0, x has to be 1, right? And so that puts me, just as I kind of had I hopefully suspected, right? Because one line given, okay? But now let's connect these and I'm gonna label them y equals 1 minus x. Right? Because then I can kind of refer to them by name. That's gonna come in handy when we go to find the intersections, right? Especially having rearranged it to be in the form of y equals mx plus b or some version of that. Makes it a little bit easier. How about for 2? 2 started at x plus 2y is less than or equal to 6. And if you wanted to, you could write a new line with x plus 2y is equal to 6, right? And then rearrange for y. Let's do 2y is equal to 6 minus x, which makes y is 6 minus x divided by 2, which in my solutions, I've been writing just as not as fractions, but as decimals, right? 6 divided by 2 makes 3, but -1 divided by 2 is -0.5 or minus 0.5. And so I get 3 minus 0.5 times x. I'll do the same thing. Right. If I plug in x equals 0, I get y must be 3. If again, this is on a scale of 1s, I get 1, 2, 3, kind of giving me a good clue about which line to be on. I'm not expecting to see your work for the points, right? As long as you're able to label them, I don't really, doesn't matter to me how you got there, but usually we need 2 points on the line to figure out how to draw it, right? And just for practice, if I set y equal to 0, right? 1/2 needs to be multiplied by 6 to make 3 minus 3, which is 0, right? And so that confirms, I hope, let me check. 1, 2, 3, 4, 5, 6. Phew. That's the point, and that makes this the line that I want. You guys really like this way better, huh, than drawing your own lines? Wow. I think it's harder. Y equals 3 minus 0.5x. Everyone's like, whoa, we didn't commit to that. That it was easier. It is hard to draw lines under pressure. Last line, by elimination, obviously, makes it the remaining line, but let's just rearrange them. We had 2x plus y is less than or equal to 6, which means y is equal to 6 minus 2x. If I plug in x equals 0, which is my go-to move, I get y equals 6, which should be this guy up here. And we can confirm if I let x be 3, then 6 minus 6 makes 0. And I'm happy with that. So this is at y equals 6 minus 2x. If I give you this as a test question, I wouldn't shade the area for you, right? Just give you the lines. You have to match them to the constraints. Probably about the same. And so how do we figure out that this is the area that we want? So first thing we want to do is we want to be above this line, this blue line. We have to be above it, right? Greater than or equal to 1. And so what that means is, and once you've seen enough of these lines, you'll know what's below and what's above. You can always take a test point, right? And just kind of something 0.5, 0.5, 0.5 plus 0.5 makes 1. Okay, maybe that's a bad one. Because that's on the line. I picked a bad one. 0.25 and 0.25? I don't want to use 0, 0, because that's boring. 0.25, 0.25 makes 0.5, which is not greater than 1, right? And so that tells me that this little point that I kind of made up on the spot here, 0.25 is not in the region. So I want to be on the opposite side of the fence. Okay. And so then I like to draw these little kind of arms pointing, hey, I want this area here. Okay. How about you talk yourself into the orange one? Aren't you glad that we've drawn it? So here, x plus 2y has to be less than or equal to 6. So let's pick a point that is on kind of this side of the line. 1, 1 might be a good point, right? I see that 1, 1 is on this side of the yellow or orange line here, right? And so if I plug in 1 plus 2 times 1, right, it's going to be 3, which is less than or equal to 6, right? And so that satisfies the criteria that I want and satisfies the constraints. And so then I put my arrows pointing down, right, kind of below it. And then finally, 2x plus y has to be less than or equal to 6. And so if I plug in 1, 1 again, right, that's on one of the sides of the purple line. So then I get 2 times 1 plus 1 is 3, which is less than or equal to 6, which is exactly what I wanted. And so then I have to be on this side of the line. Your feasible set is the area where all these things happen all at the same time, right? Everything all at once. And so here I call it I just call it FS, feasible set. And now it's our next job. Now that we have this area shaded in or just kind of as long as you know which area you want, right? You can be as particular or sloppy as you want shading them in. But what's our next step? Finding the vertices. Nice. To the next page. No, I can play it cool. I can play it cool. So here, we don't have a point at the origin, right? And so right here at 0, 0, there is no vertex at the origin. And so then let's start up here. As long as you're kind of moving methodically and I can follow how you labeled these vertices, that's fine. Okay. And so let's start here and call this A, which makes this B, C, D, and don't forget about E. Right? Make sure you catch all the corners. A, if you already kind of used it to find the point, if it's on an axis, you don't have to show the work. But if it's off the axis, then I do want to see the work. Like this point C here, I want to see the work for the intersection between those two lines. But A is at 0, 1. B, we decided was at 0, 3. C is the intersection between, oops, get caught in the loop here, between which two lines? So C is the intersection between orange and purple. And so I'll do the purple equation first between this guy. Oh. Okay, that's okay. And the orange one. Whoa. I'll just write it out. Y equals 3 minus 0.5 times x. We need to find that intersection. Gonna set these two equal to each other. 6 minus 2x is equal to 3 minus 0.5x. Move all your x's to one side and move all your non-x's to the other side. It doesn't matter which one, as long as you kind of shuffle them over. And so I like to move my x's to the left-hand side and my non-x's to the right-hand side. But if you see kind of some easier math in this scenario, for example, if you moved your x's to the right-hand side, you would get to add 2 to negative 0.5, which means you wouldn't have to deal with negatives. So once you start seeing those things and you're like, hey, I'd rather not work with negatives, right? You're allowed to avoid that. But for now, I'll keep with the same consistent procedure, okay? Which means that negative 2x plus 0.5x on the one side, and then 3 minus 6 on the other side. Which means I have 1.5x is equal to negative 3. No. What happened? X can't be negative. Oh, haha. Nice try, Emily. Negative 1.5x. We already said one of our constraints was that x can't be negative. And I was about to end up with a negative x. Doesn't work. Nice way of checking your work though, I guess. You really have to check mine. -3 divided by -1/2. Is that 4? What is that? No. Who knows? Math. 3 divided by 1/2, 2. I guess that makes sense. So now you can use either one of these lines to figure out what the y value is. You could even use both just to make sure you've got the same value. Sorry, was there a question or no? No, no, no. You're allowed to have your hands up, but if you have a question, then stop me. Let's see here. Just for simplicity, I tend to just use the first one, right? But if you see easier math coming your way with the second one, go for it. Y is 6 minus 2 times 2. So y must be 2. What I want you to do is go back to the graph and just make sure that 2, 2 checks out with what we're seeing, right? Especially if you're drawing your own axes, right? My axes are always off. And even when I'm, drawing my own lines and stuff, I can't trust that my axes will look good. And so that's why you want to always show your work for the intersections. But here, point C, it sure does. It looks like 2, 2. Usually when I teach this stuff, I make the intersections at something weird. These have all been nice whole numbers. I'll keep it that way for you guys. But we could make it all weird. But the procedure stays the same. And then D is at 3, 0, and E is at 1, 0. So D is at 3, 0, and E was at 1, 0. So the fundamental theorem of linear programming says that your profit function, or this P, is going to be maximized at one of these corners. Right? So now we evaluate this thing at each corner and figure out which one is the maximum value. Which one would we choose? And so we've got your vertex A, B, C, D, E. And 0, 1, 0, 3. This is the one we had to do work for. 2, 2. Oops. D is at 3, 0, and E was at 1, 0. Now I want to evaluate the objective function. Right? Notice how that hasn't come into play at all. You figure it out in the very beginning, and then you parking lot it until the very end. And you bring it back in. So we wanted to maximize this thing here. X is 0, Y is 1, I get 15. X is 0, Y is 3, what's that, 45? Let me just confirm, yep. X is 2 and Y is 2. Thank you. 3 and 0, 30, and I guess I shouldn't be so sloppy. I was sloppy in my solutions if the math was kind of reasonable. Okay, 15 times 1 is 15. So you can, it was a long time ago that we did this last week, so. Remind you before I let you fly on your own again. If you want to maximize, which one would you choose? C. Yeah,
joking.
but
I'm joking.
yeah, but actually do C, but then report that you were doing E and keep the skim off the top.
Ah, exactly.
That's business.
Ooh.
Oh no, we're running at E. No. Yeah, what do you mean? No. 10. That's it. I know. If I had a gold star, slap it on there.
What? That's enough.
How about this?
I'll take that.
Everyone gets one.
Yes.
How about minimization? So those are all the examples that I have for maximization, but let's look at minimization, and then you've got an assignment to do for the maximization problems. All right, so. Minimization is on the next page, and you guessed it. I want you to buddy up as much as you are comfortable doing
Oh, yeah.
and work through the problem together. And then we'll work through it together as a group. I'll pause the recording and we'll see how long we do it for. Oh, there's a chat. Oh, nice. Awesome. Thank you. Record earlier. But you guys were all here. We found the objective. This is just for the recording. We found the objective function and we defined X and Y from the objective function. You weren't here? Sorry about that. Yeah, you really missed out. Seriously. I even brought paper.
Damn.
I know. But I only printed just enough. Okay. Your constraints. So we've already incorporated the cost per hour, right? And our X's and Y's are now the number of hours that John works and the number of hours that Mary works. So we always want to map it back to those variables, right? And so let's deal with this first one that we talked or that we highlighted. And because that one's kind of sneaky, it says that each must be employed at least 1 hour a week to justify their employment. Right? And so X has to be greater than or equal to 1, and Y has to be greater than or equal to 1. I write this one down because it's not greater than 0 or X greater than 0, Y greater than 0, which is kind of our default. Now we're in a more restricted area. Okay. And then we want, he's got at least 110 papers to be graded each week. Now, John can grade 20 papers per hour, which is a good thing because we know that X is the number of hours that John works. So then the total number that he can mark in a week would be 20 times X. But we're also working with Mary, who's a fast marker. She can grade 30 papers per hour, right? So together, right, 20X plus 30Y has to be at least, and that's kind of a tricky one, I think, right? That means it's greater than or equal to 110. I'm not going to write down the X greater than or equal to 0, Y greater than or equal to 0, just because we've already restricted X and Y to be even kind of tighter. And so these are all my constraints that I can see. Did I miss any? Asking for a friend. Okay. So far, we're doing all right. How about for this line here, 20X plus 30Y, I'll reframe it as is equal to 110. And then I'm going to rearrange for Y, right, just to make it a little bit easier for myself later on. Actually, let me bump this down here. So now I get 30Y is 110 minus 20X. So Y is 110 minus 20X, all divided by 30. It's going to make a mess, I think, I suspect, from seeing it out there. 110 divided by 30 is gross. 3.667. How about this? If you have to find the intersections, you should use the fractions, right? But to draw the lines, it'll be easier to use rounded values, right? Just to get an idea, because 110 divided by 30, I don't know what that is in my kind of, it's not in my repertoire. And so let's even round just to 1 decimal place, because I'm not going to be able to draw it very closely. 20 over 30, let's say, is minus 0.7 times X. I will do kind of use rounded values. Just to draw the line. But exact values, so those exact fractions, if you need to find intersections, but exact values, which will be this one. Whoa, values. I'll say if you need to find intersections. Add a page. Oh. Okay. So let's draw these. How do I know kind of what scale I need to be including? In this case, it's not too bad, right? Because I know on my y-axis, well, y has to be greater than or equal to 1, and then my next constraint would be that y has to be kind of above 3.7. Okay. So what if I just did kind of a, I don't know, up to 6, just for fun. Can I count? 1, 2, 3, 4, 5, 6. I can. And I'll do kind of roughly the same. So this is going to be 1, 2, 3, 4, 5, 6. And I'll do roughly the same thing. If you've drawn your scale like this, you can't really rely on it to trace back and say, oh yeah, that's exactly the point that I wanted. You have to solve for the intersections. Okay. Let's deal with these constraints first. X is greater than 1. X is greater than or equal to 1 puts me here at 1. Right? And technically it goes down 2. And which side do I have to be on? Well, I can just pick values of x. X equals 2 is greater than or equal to 1. And so that means that the area that I need is going to be everything to the right of this line, right? Anything on the other side is out, right? Because then Mary's working, or John, I guess, is working less than 1 hour a week, which we're not allowing. And we do the same thing now for Mary. She has to work at least 1 hour. And same idea, right? We have to be above this line, right? Which in terms of overlap, right? You're kind of looking at these, and sometimes I'm going to erase this later because I think it's too hard to read, but you have to figure out where they all overlap. It's really hard. Another method that I have read about that I have a hard time employing is you shade the area you don't want, and then the area that's unshaded is the feasible set. Because then you can kind of, okay, I get rid of this, right? And so that would look like this is kind of cut off, and this is cut off, right? Kind of showing where you're restricted to. Again, for some reason, I have a hard time kind of getting into the groove of that. But whatever you need to do to figure out which areas you want to be in or you're constrained to is fine by me. I use these little arrows. It's a lot cleaner too. Okay. Next constraint. Oh, I guess I can be proper, Emily. Y equals 1, and this is at x equals 1. All right. That'll make it nicer when I have to find the intersections. Now let's draw the more complicated line. I'm going to use these rounded values, right? Just to get an idea of where the line goes. But then, like I said, you're going to use the exact values to find the intersections if we need them. Maybe we don't even need them. What would the line look like if we don't even need them? Maybe something below this intersection here. We wouldn't need it. But surprise, surprise, we will. Y equals 3.7 minus 0.7x. Let me just jot that down so I can refer to it on the same page. So when x is 0, y is 3.7. And I've got a pretty sloppy scale here anyways, so I'm gonna put my first point on the y-axis at 3.7. Now I have kind of all these values here. Let's see, what if I used, oops. This was 2/3, right? What if I use 3? 2/3. I guess it's easier. Or how about we just space them out? How about 5? Let's just brute force it, right? If I let x be 5, right? Let x be 5, you get y is 3.7 minus 0.7 times 5. So now here I am, and I want to figure out where on the y-axis I'm going to end up. Time will tell. 0.7 times 5, and then 3.7 minus that. I get 0.2. Okay. Let's put that somewhere here. Call that 5.2. I'm only drawing this point so that I can have 2 points on the line, right? If you're comfortable working with these fractions, it might have actually been easier to plug in and maybe solve for the y. When y is 0, what's your x? Maybe even up here. Let's do that, just to see where on the y-axis you would fall. If y is 0, then x would be 110 divided by 20, which is 5.5. So if you wanted to, you could have another point, and because my scale is so wonky, they're not probably going to line up and be on the same line. But if I had a nice, beautiful scale, right, then they should all be on the same line. All right. But wait, there's more. Okay. Which side of this line do I need to be on? Above. Nice. One way to check. This is your fence. Pick a point. Let's call it x is 3, y is 4. Seems reasonably above that point. So when x is, when x is 4, let's use this one. When x is 4, I get 80 plus, and I can't remember, 80 plus, what did I say? 3. 30 plus 90 is 170, which is greater than or equal to 10. So if this random point that we picked is satisfying the constraint, then they all will above this line on that side. I'll remove that point because it doesn't contribute. Okay. So now let's try it with shading out the areas you don't want. No, shading in the areas you do want. Oh boy. Okay. Shading in the areas you do want. Feeling cute, might delete later. Yikes. I don't know, I don't find that very helpful at all. Where do they all overlap?
I didn't think you were gonna color in the whole sections, cause I just did a little.
Yeah, that's cute.
Never do that again.
It hurts. How about, what if we kind of lob off the areas we don't want? You'll still be left with the areas you had, but it might be kind of nicer to look at a little bit. So now your feasible set, I'm just going to kind of frame it in here. Ugh. And if you got to the feasible set without any crazy shading, looking at you, kid, you don't have to do any shading. Okay? And so as long as you get to the feasible set, that's the goal. Right? Now, I guess I need to put a label on this thing. Y is 110, 110 minus 20x over 30. Remember, for finding the intersections, you're going to use the exact values, right? Use the full fractions. So that's why I'm labeling it like that. Okay. Minimization problems will have shapes like this. They're unbounded regions. We're used to having kind of going from 0, 0, and then just kind of sprouting out as far as we can go for maximization problems, right? But now we're working in this unbounded region, which makes it a little bit trickier because it's possible to not have a solution anymore. But that's for another course. Let's use that cop out. Not for us. And this is your feasible set. Now, before I take all the fun away from you, you have to find the intersections. Let's label them so we're all talking about the same things. But if I go from here, this keeps going and going and going, technically till infinity, right? We're allowed to employ her, or I guess, yeah. Y can keep going for as long as we need it to. There is a limited number of hours per week, so there is an upper bound, but they didn't mention it, so guess she could hire someone, hire out her work, anyways, whatever. And so this area keeps going and going and going and going. And so here, my first intersection, I'm gonna say is right here. This is where I go against my clockwise. Now I move counterclockwise for some reason. I kind of move from the highest point around counterclockwise. If you started at the next vertex, that's fine too. I'm happy with that. In this case, I only find 2 vertices. So as long as you label them, I'm happy. And obviously, John can only work so many hours in a week, only so many exist, right? But we're trying to minimize the cost, right? Not work them to the bone all the time. So that's why it's not really going to be an issue. I'll give you a moment to find the intersections using the fractions, right? A and B. And I'll pause this recording. Resume. It's gonna be a pretty choppy recording. I like to write it out in words that A is the intersection of, let's do the big nasty one first. Y equals 110 minus 20x over 30. Oops, clean that up. And which line? And this one, right? For A, and x equals 1. If I just have a nice x equals 1 or y equals 1, then you can just plug those values into the other equation and solve for the other value. And so if y is 110 minus 20x divided by, and maybe divided by 30, I'll just replace this x with 1 right away. I get 110 minus 20, which is 90. 90 divided by 30 is 3. We forced x to be 1, right? All on that line, x has to be 1. And so then the intersection is at 1, 3. That's a nice number. And that's why I want you to use the exact values, so with the fractions, right? Because otherwise you're going to get kind of slightly off numbers. And B is the same thing, but the intersection between oops. I'm just gonna copy this because I can. And y equals 1. Same deal, but now I'm going to swap in y equals 1 and solve for x, which is a smidge more work. Oops, 110 minus 20x over 30. I'm going to float that 30 over to the left-hand side. And so then I have 30 times 1, which is 30. It's 110 minus 20x. Solving for x, I'm going to keep the x on the right-hand side for a little bit longer and subtract 110 from 30. 30 minus 110. Keep wanting to skip writing some stuff here. I get negative 80 is negative 20 divided by x. So x must be negative 80 divided by negative 20. Those negatives will cancel out. And I get x must be 4. Which makes my intersection at 4, 1. I force y to be 1. Now we only have 2 intersections. I still like to set up the table, just same procedure always. So I've got a vertex A and B at 1, 3, and 4, 1. And I want to minimize the cost, right? So again, this is the, I guess I'm taking away the glory. Sorry. But I can't stop. We want to minimize the cost, which we said way, way, way back. Haven't touched it since. 15 times x and 20 plus 25 times y. Do a little line here. So in this first vertex, I have 15 times 1 plus 25 times 3. That one, that combination, which is John works for 1 hour and Mary works for 3 hours, right? She's a little bit more expensive, but she also marks faster, right? And so 15 plus 25 times 3 puts me at, it's gonna cost me 90 units, dollars, I guess. And the next combination is, instead of that, I make John mark for 4 hours, and then I bring in my my more expensive marker for only 1 hour. 15 times 4 is 60 plus 25. That's gonna cost me $85. Now, if I get to choose, right, I'm going to choose B. Poor Mary, or maybe poor John, because he has to mark a lot more. Did I do something wrong?
No, I just put A and B as different points.
Oh,
Like I just,
that's okay. As long as, yeah. So now, this is the minimum, which is what I wanted. I like to do a little, therefore, the cost is minimized to $85. Pretty cheap. Maybe I should buy markers or hire markers. I think they charge more now. I think it was like 30 bucks an hour when I was going to school. Pretty good. The cost is minimized to $85 when John, oops, when John marks for 4 hours and Mary for 1 hour, I guess. Nice. So like I said, same procedure as always. The difference is the feasible set, or kind of the typical shape of the feasible set for a minimization problem is going to be kind of, okay, you can start down here and then you can move all the way up into infinity. Yeah. What are we gonna do about this one? You're gonna start it, which is the last page. You guys go. It got all weird. I did kind of an old school, new school, old school print job. I didn't feel like typing all these out. What's kind of funny, I think, is the restrictions that we have, or the constraints that we have. Yeah. Pardon? Oh, yeah. Can I stop the recording? It's like pausing a show with just like 2 minutes left, but a minute and a half is the credits. So we'll use this example for review, but because you've been working on it, you can check your work. Make sure that you got those vertices. Then that should be all you really need. And if you have any questions, let me know. Otherwise, I'll see you Thursday.
I'll see you there.